What if the world we live in today had been shaped by inventions that should have existed centuries ago? Picture towering medieval cities powered by machines far ahead of their time, or ships crossing oceans with navigation tools lost to history. The Middle Ages weren't just an era of castles and feudalism, they were a hotbed of innovation, where brilliant minds crafted technologies so advanced they could have rewritten the course of human progress. Yet somewhere along the way, these breakthroughs vanished, buried under the dust of time. Today, we're uncovering 25 of these forgotten marvels, each one a glimpse into what might have been. Think about how different our modern lives would be if even a handful of these inventions had survived. Some were suppressed by rulers fearing change, others lost to war or simply forgotten as knowledge slipped through the cracks of history. But what's truly astonishing is how close we came to an entirely different timeline, one where the Industrial Revolution could have dawned in the 1400s instead of the 1800s. These weren't just crude prototypes, they were fully functional designs, some rivaling the sophistication of machines from centuries later. From mechanical clocks that predicted celestial events to architectural techniques that defied the limits of medieval engineering, the past holds secrets that still leave experts in awe. This isn't just a story of what was lost, it's a reflection on how fragile progress can be. Every one of these technologies carries a lesson about the precarious nature of innovation and how easily brilliance can fade if it isn't nurtured. As we journey through these 25 lost marvels, you'll discover inventions that could have transformed medicine, transportation, even warfare, centuries before they finally re-emerged. Some were so far ahead of their time, it's almost as if they belonged to another world entirely. So let's step into the shadows of history and uncover the tools, machines, and ideas that might have changed everything if only they'd been given the chance. Imagine a weapon so fearsome that entire fleets would retreat at the mere sight of its flames, a liquid fire that clung to ships, burning even on water, impossible to extinguish. This was Greek fire, the Byzantine Empire's most closely guarded secret and one of history's most devastating lost technologies. Developed around the 7th century, it wasn't just a weapon, it was a psychological terror, striking dread into the hearts of enemies who had no defense against its unstoppable blaze. The Byzantines deployed it through pressurized tubes mounted on their ships, spraying streams of fire that could turn the sea itself into an inferno. For centuries, this fearsome advantage kept invaders at bay, securing Constantinople's dominance over the Mediterranean. But what made Greek fire so extraordinary wasn't just its destructive power, it was the sophistication behind it. Modern chemists still debate its exact formula, but clues suggest it likely contained a mix of crude petroleum, pine resin for stickiness, and possibly quicklime, which ignites on contact with water. Some accounts even mention a mysterious, wet fire that burned brighter when doused, hinting at chemical reactions far ahead of their time. The Byzantines guarded this knowledge with obsessive secrecy, known only to a select few artisans and the imperial family. When Constantinople finally fell to the Ottomans in 1453, the recipe vanished with the last keepers of the flame, leaving behind only legends and charred remnants of its terrifying legacy. Had this technology spread beyond Byzantium's walls, it could have reshaped the course of warfare centuries before gunpowder revolutionized battlefields. Picture medieval armies wielding portable flamethrowers or fortified cities defended by fire-spewing engines, an entirely different path for military innovation. Beyond warfare, the chemistry behind Greek fire might have accelerated advancements in alchemy and early industrial processes. Its loss wasn't just a setback for weaponry, it was a missed opportunity to unlock the secrets of combustion and energy centuries earlier. The story of Greek fire is a stark reminder of how fragile human knowledge can be, and how one empire's obsession with secrecy might have cost the world a leap forward in science and technology. While Greek fire was terrifying enemies on the battlefield, another lost technology was quietly holding up the very foundations of civilization: Roman concrete. Unlike the crumbling mortar of medieval castles, Roman structures like the Pantheon and aqueducts still stand strong after 2,000 years, defying time, earthquakes, and even seawater. The secret, a revolutionary mix of volcanic ash, lime, and crushed rock that didn't just harden underwater. It grew stronger with each passing century. Medieval builders, relying on weaker mixtures, could only dream of such resilience. If this formula hadn't vanished with Rome's collapse, the Middle Ages might have been an era of unshakable fortresses and soaring towers, reshaping the skyline of history. The magic of Roman concrete lay in its chemistry. Modern scientists discovered that the volcanic ash, known as pozzolana, reacted with seawater to form rare minerals that reinforced the material over time. This self-healing property meant cracks actually repaired themselves, a feature modern engineers are only now replicating with high-tech lab materials. Meanwhile, medieval cathedrals and walls crumbled under their own weight, their builders unaware that the answer had already been invented and forgotten. Imagine the impact if castle architects had access to this knowledge. Coastal defenses could have withstood endless sieges, bridges spanned wider rivers, and harbors resisted erosion for generations. Even early skyscrapers might have risen centuries sooner, their foundations as unyielding as Roman breakwaters. Yet the loss of this technology hints at a deeper truth: progress isn't inevitable. When Rome fell, entire libraries of engineering knowledge burned or molded away, leaving later generations to rediscover what had once been common practice. It wasn't until 2023 that researchers fully decoded the ancient recipe, proof that some innovations are so advanced, they slip through history's fingers not once but twice. The story of Roman concrete isn't just about buildings. It's a warning about how easily humanity's greatest achievements can turn to dust when knowledge isn't passed down. Had medieval stonemasons inherited this legacy, our world might stand on far sturdier ground. Buried beneath the waves for over 2,000 years, the Antikythera Mechanism wasn't just a relic, it was a revelation. When divers stumbled upon its corroded fragments in a shipwreck off Greece in 1901, they assumed it was just another artifact. But as the layers of encrusted time were painstakingly removed, scientists uncovered something astonishing: an intricate network of bronze gears, precisely arranged to model the movements of the sun, moon, and planets. This wasn't a simple calendar, it was a mechanical computer capable of predicting eclipses, tracking Olympic cycles, and even accounting for the irregular orbit of the moon. The sophistication of its design wouldn't be matched again until the mechanical clocks of the 14th century, leaving historians to wonder, was this a one-of-a-kind marvel, or did similar devices exist in the shadows of medieval Europe? The Antikythera Mechanism's genius lay in its miniaturization of cosmic patterns. Tiny gear teeth, some as thin as a millimeter, replicated the celestial dance with startling accuracy, a feat that would require advanced mathematical knowledge and metallurgical skill. But here's the haunting question: if ancient Greeks could engineer such a device by the 1st century BCE, why did it take over 1,000 years for comparable technology to reappear? Fragmented records suggest medieval monasteries might have housed fragments of this knowledge. Manuscripts from the court of Charlemagne mention an astronomical machine, while Arab scholars like al-Biruni wrote of geared devices for calculating star positions. Yet none survived intact, lost to fires, wars, or perhaps deliberate suppression by authorities wary of challenging the Church's cosmic authority. Imagine a world where these mechanical computers had been refined instead of forgotten. Monasteries could have become medieval data centers, their scribes tracking comets and planetary alignments with precision. Navigators might have carried portable celestial calculators, transforming exploration long before the age of Columbus. Most tantalizing of all, the scientific revolution, with its reliance on empirical observation and mechanical models, could have blossomed in the 1200s instead of the 1600s. The Antikythera Mechanism proves that the seeds of the modern world weren't planted in the Renaissance. They were buried, waiting for someone to rediscover what had already been invented. Its loss wasn't just a setback for astronomy, it was a theft of time itself, robbing humanity of centuries of progress. In the clash of steel during the Crusades, one weapon inspired both terror and awe: the shimmering, water-patterned blades of Damascus steel. European knights watched in disbelief as these swords cleaved through their finest armor, remaining razor-sharp after battles that would leave other blades notched and dull. But these weren't just superior weapons, they were masterpieces of metallurgy, forged from a secret process that vanished by the 1700s, taking with it knowledge that could have transformed the medieval world. The mystery of Damascus steel begins with its raw material, Wootz ingots imported from India and packed with microscopic carbon nanotubes, a nanostructure modern scientists only identified in the 1990s. Blacksmiths heated, folded, and hammered this steel in precise cycles, creating layers so fine they resembled flowing water under the surface. The result: blades that weren't just harder than anything Europe could produce. They were nearly unbreakable, with a flexibility that absorbed shocks and an edge that resisted wear for generations. Contemporary accounts tell of swords bending 90 degrees without snapping, then springing back straight, a feat unmatched until modern alloy research. Imagine if this technology hadn't faded into legend. Beyond swords, Damascus techniques could have produced plowshares that never dulled, saw blades that cut stone like wood, or clock springs that kept perfect time for decades. The Industrial Revolution might have arrived earlier, powered by machinery built with this resilient steel. Yet the knowledge disappeared, likely lost when trade routes shifted or master smiths took their secrets to the grave. Modern attempts to recreate Damascus steel have only yielded approximations, proof that some medieval artisans achieved a perfection we still can't fully replicate. Their forgotten craft wasn't just art, it was a blueprint for a stronger, more durable world, one that slipped through history's fingers when we needed it most. Centuries before coal-powered factories belched smoke across the English countryside, a brilliant inventor in 1st century Alexandria had already unlocked the secret of steam power. Hero of Alexandria's Eolipile wasn't just a curiosity, it was the world's first working steam engine, a spinning bronze sphere propelled by jets of vapor. Yet instead of revolutionizing industry, it became a party trick for wealthy patrons, a marvel to amuse dinner guests as it whirled on banquet tables. This wasn't a failure of engineering, it was a failure of imagination. The ancient world held the spark of an industrial revolution in its hands and let it flicker out. Hero's design was deceptively simple. Water heated in a sealed chamber forced steam through angled pipes, creating thrust that spun the sphere at dizzying speeds. The same basic principle would later drive locomotives and power plants, but in Hero's era, no one saw beyond the spectacle. Medieval Islamic scholars like al-Jazari came closest to grasping its potential, adapting steam to pump water and automate clocks in 12th century Syria. His book of knowledge of ingenious mechanical devices detailed piston pumps and valve systems eerily similar to those used in 18th century steam engines. But without a culture of mass production or urgent need for mechanization, these inventions remained beautiful oddities rather than world-changing tools. Picture an alternate 1300s where blacksmiths harnessed steam hammers or textile mills spun cloth with steam-driven looms. The ripple effects would have been staggering. Cities might have industrialized before the Black Death, reshaping economies and societies centuries early. Ships could have crossed oceans without relying on unpredictable winds, accelerating global trade and exploration. Even warfare would have transformed, with steam-powered siege engines reducing castle walls to rubble in days instead of months. The ingredients were all there: Hero's prototype, Al-Jazari's refinements, and medieval Europe's growing demand for labor-saving machines. All that was missing was the vision to connect them. The tragedy of Hero's engine isn't just that it was forgotten, it's that the knowledge resurfaced repeatedly without ever catching fire. Byzantine engineers used steam to power temple doors that seemed to open miraculously, while Renaissance thinkers like Leonardo da Vinci sketched steam-powered cannons. Each time, the technology slipped back into obscurity, not for lack of capability, but because societies couldn't yet conceive of a world beyond muscle and water wheel. It took until 1790 for James Watt to commercialize what Hero had demonstrated 1700 years earlier, proof that innovation doesn't just require invention, but an entire civilization ready to embrace it. The steam engine wasn't lost, the future it promised was. The Norse sagas tell of a mysterious tool that guided Viking ships through fog and storms, sunstones, crystals capable of revealing the sun's position even when the sky was shrouded in clouds. These weren't mythical objects but likely pieces of calcite or cordierite, minerals that polarize sunlight, allowing navigators to pinpoint its location with eerie accuracy. While modern compasses rely on Earth's magnetic field, the Vikings harnessed the physics of light itself, turning crystal clarity into a maritime superpower. Had this technology spread beyond Scandinavia, the age of transatlantic exploration might have begun not in 1492, but in the 900s, rewriting the map of history. What made Sunstones so revolutionary was their simplicity and reliability. By rotating a translucent crystal until its double refraction aligned with scattered sunlight, navigators could trace the sun's path across obscured skies. Icelandic spar, a type of calcite found in Viking trade routes, produces a telltale doubling effect when held at the correct angle, a natural GPS hidden in plain sight. Archaeological evidence supports the sagas. A shipwreck discovered off Alderney in the Channel Islands contained a calcite crystal near navigational tools, its edges worn smooth from repeated use. This wasn't guesswork, it was precision engineering disguised as nature's gift. Imagine the consequences if Mediterranean or Arab traders had adopted this technology. Viking ships reached Newfoundland around the year 1000, but without widespread knowledge of sunstones, these voyages remained isolated feats rather than the start of sustained global trade. European explorers like Columbus still struggled with dead reckoning and unreliable compasses 5 centuries later, their crews terrified of veering off course into the unknown. With sunstones, the Indian Ocean spice trade might have been dominated by Norse merchants, and African or Asian civilizations could have encountered European goods centuries earlier. The delay wasn't just a matter of geography, it was a bottleneck of lost knowledge, one that kept continents separated far longer than necessary. Yet the Vikings guarded their secret closely, passing it down orally rather than in texts, leaving later generations to dismiss sunstones as legend. By the time scholars like René Descartes theorized about polarized light in the 1600s, the technique had vanished, its practitioners lost to time. Modern experiments prove the concept works flawlessly. A team from Hungary's Eötvös University successfully navigated cloudy skies using nothing but a piece of calcite, confirming what the Norse had mastered a millennium earlier. The tragedy isn't just that the technology disappeared. It's that the world spent half a millennium fumbling in the dark when the solution had already been held up to the light. Deep in the vaults of Baghdad's National Museum lies an object that shouldn't exist, a small clay jar no larger than a fist, dating back to the Parthian Empire around 2,000 years ago. Inside, a copper cylinder surrounds an iron rod sealed with asphalt, a design so suspiciously modern that when German archaeologist Wilhelm Koenig uncovered it in 1936, he could only conclude one thing: this was a battery. Not the kind we recognize today, but a rudimentary voltaic cell capable of generating electricity through chemical reaction. Fill it with vinegar or grape juice, and the jar could produce around 1 volt of power, enough to electroplate jewelry or create mild tingling sensations. But here's the haunting twist. If this technology was known in the ancient world, why did it vanish for nearly 2 millennia before being reinvented in the 1800s? The Baghdad battery wasn't an isolated fluke. Similar artifacts have surfaced across Mesopotamia, suggesting these devices might have been more than ceremonial curiosities. Medieval Persian alchemists wrote of vessels that bite without teeth, containers that produced strange sparks when filled with acidic solutions. Even the legendary Library of Alexandria housed scrolls describing lightning in a jar, though those texts burned before their secrets could be deciphered. The real tragedy isn't just that these batteries existed, it's what they could have become. Picture 9th century Baghdad illuminated by primitive arc lamps, or monasteries using electrified vats to purify metals. With incremental improvements, these clay jars might have evolved into power sources for early scientific instruments, accelerating discoveries in magnetism and chemistry centuries ahead of schedule. Yet the Baghdad battery's potential wasn't just about electricity. It was about the mindset that could have grown around it. Ancient and medieval thinkers often saw natural phenomena as mystical forces, not something to be harnessed. But imagine if alchemists, with their obsession for transformation, had recognized the link between these tingling jars and the lightning streaking across the sky. The very language of science might have shifted earlier, replacing spirits and humors with circuits and currents. Instead, the knowledge fragmented, leaving behind only cryptic references and enigmatic artifacts. By the time Alessandro Volta stacked his first metal discs in 1800, the world had spent 1,500 years reinventing what Mesopotamian artisans already held in their hands. What's most striking isn't the technology itself, but how close humanity came to an electrified Middle Ages. These jars weren't dead ends, they were seeds. Seeds that could have grown into telegraphs without waiting for Morse, or electromagnets without relying on Faraday. The Baghdad battery proves that innovation doesn't always move forward. Sometimes it lies dormant, waiting for the right moment or the right mind to wake it up again. Its legacy isn't just a forgotten power source. It's a testament to how differently history could have unfolded if just one idea had been nurtured instead of buried. In the year 132, as Roman engineers were perfecting their aqueducts, a Chinese polymath named Zhang Heng unveiled something extraordinary, a bronze vessel adorned with 8 dragon heads, each clutching a metal ball above the jaws of 8 corresponding toads. This wasn't ceremonial art, it was the world's first seismoscope, a device so sensitive it could detect earthquakes hundreds of miles away. When tremors struck, an internal pendulum would tilt toward the quake's origin, triggering a mechanism that dropped a ball from a dragon's mouth into the toad below, pinpointing the direction of disaster. Court records from the Han Dynasty describe it accurately predicting a quake the capital couldn't yet feel, saving lives by giving distant provinces precious hours to prepare. The genius of Zhang Heng's design lay in its elegant simplicity. Unlike modern seismographs that rely on electronic sensors, his device used inertia and gravity, principles so universal they'd work flawlessly even today. Historians long debated how it functioned until 2005, when a team from the Chinese Academy of Sciences built a replica using 8th century materials and techniques. Their version detected simulated quakes with startling accuracy, proving the original wasn't just legend, it was cutting-edge science cloaked in ancient craftsmanship. Medieval Europe, meanwhile, still attributed earthquakes to divine wrath or mythical creatures stirring underground. Imagine if knowledge of the seismoscope had traveled the Silk Road. Monasteries dotting seismic zones like Italy or Greece could have maintained networks of these devices, creating the world's first early warning system centuries before Richter scales existed. The cost of this lost technology becomes tragically clear when you examine disasters like the Lisbon earthquake of 1348. Without warning, tremors toppled cathedrals and sparked fires that burned for days, killing tens of thousands. Had Portuguese sailors traded with Chinese ports and brought back seismoscope designs, Lisbon's rulers might have recognized precursor tremors and evacuated the city. Even rudimentary awareness of seismic patterns could have reshaped medieval architecture, inspiring builders to adopt earthquake-resistant techniques like those used in Japan's pagodas, which flex rather than crumble. Instead, Europe spent centuries rebuilding after each disaster, unaware that the solution had already been invented and forgotten on the other side of the world. Zhang Heng's invention wasn't just ahead of its time, it was a missed opportunity to redefine humanity's relationship with natural forces. While his seismoscope faded into obscurity, later scholars like the Persian polymath al-Biruni theorized about earthquake waves in the 11th century, and Leonardo da Vinci sketched devices to measure ground movement in the 1500s. But without a working model to build upon, these ideas remained theoretical. It wasn't until 1880 that the first modern seismograph emerged, a delay of over 17 centuries. The story of the seismoscope isn't just about a clever gadget. It's a reminder that progress isn't linear. Sometimes the brightest sparks of genius flicker out, leaving later generations to stumble toward the same truths in the dark. Had this one invention survived its journey westward, the medieval world might have faced disasters not with prayer, but with preparation. Picture the terror of Roman sailors during the siege of Syracuse in 212 BCE. Their mighty quinquiremes suddenly jerked skyward by an invisible force, then dashed against the rocks like toys. This was the work of Archimedes' claw, a monstrous defensive weapon that turned the sea itself into a death trap. Mounted on the city's walls, the device used a system of counterweights and pulleys to reach down with a giant iron hook, snatch enemy ships from the water, and flip them into splinters. Ancient historians like Polybius described entire fleets fleeing at the sight of Syracuse's harbor, where the very waves seemed to rise up against them. Yet when Archimedes fell to a Roman soldier's sword, his brilliant war machine vanished from history, leaving medieval engineers to reinvent the wheel, quite literally, when it came to heavy lifting. What made the claw revolutionary wasn't just its destructive power, it was the engineering principles behind it. Archimedes had mastered compound pulley systems and leverage to multiply human strength exponentially, allowing a few operators to hoist ships weighing tens of tons. These same mechanics could have transformed medieval construction, enabling cathedrals to rise faster with precision-lifted stone blocks, or allowing castles to deploy drawbridges and portcullises with unprecedented speed. Venetian shipbuilders might have dry-docked galleys for repairs with claw-inspired cranes, while mining operations could have extracted deeper ores using reinforced lifting platforms. Instead, Europe spent centuries relying on ramps, ropes, and sheer manpower methods the ancient Greeks had already rendered obsolete. The loss becomes even more striking when you consider the claw's potential evolution. Islamic engineers during the Crusades developed similar counterweight trebuchets, proving the medieval world was ready for advanced mechanics. Had Archimedes' blueprints survived, these principles might have merged into cranes capable of building skyscrapers centuries early, or siege engines that could dismantle fortress walls beam by beam. Even agriculture could have benefited. Imagine water wheels paired with claw mechanics to lift irrigation channels over hillsides, turning arid lands fertile. The real tragedy isn't that the claw disappeared, it's that its underlying ideas had to be painfully rediscovered rather than built upon. When Renaissance engineers like Brunelleschi studied ancient texts to construct Florence's dome, they were piecing together fragments of knowledge that should never have been lost. Proof that Archimedes' death didn't just end a life, it broke a chain of innovation that took a millennium to repair. While medieval lords huddled under firs in drafty stone castles, the Romans had solved winter's chill 2,000 years earlier, with hypocausts, an ingenious central heating system that pumped warmth through the floors and walls of villas, bathhouses, and even ordinary apartments. Picture walking barefoot on heated marble in the dead of winter, or lounging in a toasty library while snow fell outside. This wasn't luxury for emperors alone. Even modest Roman towns boasted public baths where citizens soaked in reliably warm pools, thanks to a network of raised floors and hollow walls channeling hot air from furnaces. Yet after Rome's fall, this technology vanished so completely that medieval Europeans assumed such comfort was impossible, resigning themselves to smoky hearths and perpetual damp that rotted their homes and lungs alike. The hypocaust's brilliance lay in its elegant engineering. Slaves or servants stoked wood-fired furnaces, heating air that circulated through brick channels beneath mosaic floors before escaping through strategically placed roof tiles. Terracotta box tiles lining the walls created further insulation, turning entire structures into radiant heaters. Modern tests show these systems could maintain rooms at a steady 70 degrees Fahrenheit even in freezing weather, a feat unmatched until the 19th century. But beyond comfort, hypocausts had hidden benefits. They reduced mold and respiratory diseases by keeping walls dry, allowed larger windows without icy drafts, and even enabled multi-story buildings with consistent warmth, something medieval architects struggled to achieve even in fortresses. Had this knowledge survived, the cold stone towers of medieval Europe might have transformed into livable spaces year-round. Monasteries could have preserved fragile manuscripts in warm, dry scriptoria instead of battling mildew. Hospitals might have adopted Roman heating to improve patient survival rates during brutal winters. Most intriguingly, hypocaust principles could have evolved into early industrial applications. Imagine blast furnaces preheated by hypocaust channels, or greenhouses extending growing seasons with underground heat. The Romans themselves experimented with this, using hypocausts to force ripened fruit for wealthy patrons. Yet the system's disappearance wasn't accidental. Hypocausts required meticulous craftsmanship, precise slopes in flooring to ensure even heat distribution, specialized tiles to withstand expansion skills that faded as Rome's economy collapsed. Medieval Europe lacked the infrastructure to maintain such complexity, viewing centralized heating as decadent in a world focused on survival. By the time wealthy Venetians rediscovered underfloor heating in the 1300s, they assumed it was a new invention. The real tragedy: fragments of the technology persisted in places like Moorish Spain's hammams and Byzantine monasteries, but without the systemic knowledge to revive it fully. For 1,000 winters, humanity shivered in ignorance, unaware that the solution had already been invented, then forgotten. What makes the Hypocaust's loss particularly poignant is how close medieval Europe came to reinventing it. Cistercian monks developed warming rooms with heat channeled from kitchens, while Korean ondol systems strikingly similar to Hypocausts flourished continuously since antiquity. Had these ideas crossed paths, the Dark Ages might have been decidedly warmer. Instead, the Hypocaust became a ghost in the ruins, its broken tiles hinting at a comfort the medieval world couldn't quite grasp. When modern radiant heating emerged in the 1800s, engineers believed they'd pioneered something unprecedented. In truth, they were simply relearning what the Romans had mastered and then lost centuries before. Held in the dim light of a museum case, the Lycurgus Cup looks unremarkable until a beam of sunlight hits it, transforming the green glass into a glowing ruby red. This 4th century Roman artifact isn't just beautiful, it's a scientific marvel embedded with gold and silver nanoparticles so tiny they interact with light at the quantum level. To the naked eye, these particles are invisible, less than 1,000th the width of a human hair, yet they scatter light in a way that alters the cup's color depending on the observer's angle. Modern labs only began manipulating matter this small in the 20th century, yet Roman artisans achieved it 1,600 years earlier, crafting a material that wouldn't be understood again until the invention of electron microscopes. What makes the cup truly revolutionary isn't just its appearance, it's the precision behind its creation. Researchers analyzing the glass found a meticulous ratio of gold to silver, approximately 3 parts gold to 7 parts silver, ground into particles between 50 and 100 nanometers in size. This wasn't accidental. It required an understanding of metallurgy and chemistry far beyond what medieval alchemists ever achieved. The process likely involved dissolving gold in glass melt, then carefully reheating it to precipitate nanoparticles, a technique that would later form the basis of modern nanotechnology. Had this knowledge passed to medieval glassmakers, the towering stained glass windows of Gothic cathedrals might have shimmered with dynamic hues, shifting from blue to violet as worshippers moved through the nave. Beyond artistry, the implications for science are staggering. Roman opticians could have developed lenses that filtered specific light wavelengths, paving the way for early microscopes or telescopes. Imagine 13th century scholars peering at microorganisms through Lycurgus-inspired glass, or navigators using color-shifting lenses to gauge the sun's position through fog. Even medicine might have advanced. Nanoparticles similar to those in the cup are now used in cancer treatments to target tumors with pinpoint accuracy. Instead, the recipe vanished with Rome's fall, leaving medieval artisans to puzzle over fragments of dichroic glass without grasping their secret. The cup's survival hints at a tantalizing possibility. Was this a one-off masterpiece or part of a broader tradition? Byzantine texts mention chameleon glass that changed color in imperial palaces, while Islamic scholars described vessels that gleamed differently by candlelight. Yet no medieval European glassmaker came close to replicating the effect, not for lack of trying. Venetian glassblowers, the finest of their age, produced exquisite crystallo glass but never unlocked nanoparticle dispersion. It took until 1990 for researchers at the British Museum to decode the cup's secrets using advanced spectroscopy, proving that ancient craft sometimes surpassed medieval science. The Lycurgus Cup is more than a relic. It's a window into a road not taken. Its technology could have bridged the gap between art and science centuries before the Renaissance, merging beauty with function in ways that might have accelerated optics, materials science, even chemistry. Instead, it became a solitary marvel, a reminder that progress isn't just about discovering new things, it's about holding onto them. When modern scientists use nanoparticles to create smart windows or medical sensors, they aren't inventing something new. They're finally catching up to the Romans. Centuries before coal-powered factories belched smoke across the English countryside, a brilliant inventor in 1st century Alexandria had already unlocked the secret of steam power. Hero of Alexandria's Eolipile wasn't just a curiosity, it was the world's first working steam engine, a spinning bronze sphere propelled by jets of vapor. Yet instead of revolutionizing industry, it became a party trick for wealthy patrons, a marvel to amuse dinner guests as it whirled on banquet tables. This wasn't a failure of engineering, it was a failure of imagination. The ancient world held the spark of an industrial revolution in its hands and let it flicker out. Hero's design was deceptively simple. Water heated in a sealed chamber forced steam through angled pipes, creating thrust that spun the sphere at dizzying speeds. The same basic principle would later drive locomotives and power plants, but in Hero's era, no one saw beyond the spectacle. Medieval Islamic scholars like Al-Jazari came closest to grasping its potential, adapting steam to pump water and automate clocks in 12th century Syria. His book of knowledge of ingenious mechanical devices detailed piston pumps and valve systems eerily similar to those used in 18th century steam engines. But without a culture of mass production or urgent need for mechanization, these inventions remained beautiful oddities rather than world-changing tools. Picture an alternate 1300s where blacksmiths harnessed steam hammers or textile mills spun cloth with steam-driven looms. The ripple effects would have been staggering. Cities might have industrialized before the Black Death, reshaping economies and societies centuries early. Ships could have crossed oceans without relying on unpredictable winds, accelerating global trade and exploration. Even warfare would have transformed, with steam-powered siege engines reducing castle walls to rubble in days instead of months. The ingredients were all there: Hero's prototype, Al-Jazari's refinements, and medieval Europe's growing demand for labor-saving machines. All that was missing was the vision to connect them. The tragedy of Hero's engine isn't just that it was forgotten, it's that the knowledge resurfaced repeatedly without ever catching fire. Byzantine engineers used steam to power temple doors that seemed to open miraculously, while Renaissance thinkers like Leonardo da Vinci sketched steam-powered cannons. Each time, the technology slipped back into obscurity, not for lack of capability, but because societies couldn't yet conceive of a world beyond muscle and water wheel. It took until 1790 for James Watt to commercialize what Hero had demonstrated 1700 years earlier, a proof that innovation doesn't just require invention, but an entire civilization ready to embrace it. The steam engine wasn't lost, the future it promised was. Buried in the ruins of an Assyrian palace, a small piece of rock crystal might have rewritten the history of science. The Nimrud lens, dating back to 700 BCE, isn't just a polished stone, it's a carefully ground oval that can magnify objects up to 3 times their size when held at the right angle. Discovered in 1850 by archaeologist Austin Henry Layard, this palm-sized artifact bears the telltale marks of deliberate craftsmanship, precise curvature, smoothed edges, and optical properties that blur the line between ornament and tool. To the untrained eye, it's a curiosity, but to historians of technology, it's a haunting question. Was this the world's first microscope, abandoned before it could reveal the invisible? The lens's potential becomes clear when you consider its context. Assyrian craftsmen were masters of intricate seal carvings and delicate ivory work tasks that would benefit enormously from magnification. Cuneiform tablets from Nineveh's royal libraries even describe seeing stones, used to examine fine details in textiles and jewelry. Yet what if this technology had evolved beyond luxury goods? Picture medieval monasteries with lenses mounted on stands, allowing scribes to inspect the swirling patterns of ink on parchment or the intricate veins of medicinal herbs. With slight improvements in grinding techniques, something well within the capabilities of Islamic opticians like Alhazen in the 11th century, these crude magnifiers could have become the first compound microscopes, revealing a world beyond human vision centuries before Antony van Leeuwenhoek peered at bacteria in 1670. The implications for medicine alone are staggering. Medieval doctors blamed illness on bad air or divine punishment, unaware that pathogens swarmed in every drop of contaminated water. With lens technology refined just a bit further, they might have spotted microorganisms wriggling in plague-ridden fluids, revolutionizing hygiene long before germ theory. Imagine 14th century surgeons sterilizing instruments after seeing microbes crawl on their blades, or quarantine measures implemented not out of superstition but concrete evidence. Even agriculture could have transformed farmers selecting seeds under magnification for robustness, or beekeepers observing pollen collection up close to boost harvests. The difference between the Nimrud lens and a true microscope wasn't a gap in capability. It was a lack of sustained curiosity. What's most frustrating is how close later societies came to bridging that gap. Roman naturalist Pliny the Elder wrote of Nero using an emerald to watch gladiator games, possibly a primitive corrective lens. Byzantine physicians prescribed glass spheres filled with water to magnify small objects, while medieval Arab opticians like Ibn Saul mathematically described how curved surfaces bend light. Yet no one combined these insights into a systematic study of magnification. The lens remained a novelty, its potential locked away like the Assyrian palaces where it was found. When modern archaeologists finally dusted it off, they weren't unearthing just an artifact, they were holding a road not taken, one that might have led humanity out of the dark ages of disease and into the light of discovery far sooner. The story of the Nimrud lens isn't about a single object, it's about the fragile nature of scientific momentum. For every invention that changes the world, there are dozens that languish in obscurity, not because they didn't work, but because no one recognized their significance. This palm-sized piece of crystal could have been the spark that ignited a biological revolution, turning medicine from guesswork into precision. Instead, it sat buried for millennia, waiting for a future that had to reinvent what the past already held. While medieval travelers slogged through muddy ruts that turned to quagmires with every rain, Roman merchants had raced along highways so well built, some remain usable 2,000 years later. The secret wasn't just in the cobblestones you see on the surface, it was the hidden engineering beneath. Roman roads were constructed like layer cakes of innovation. A trench packed with sand for drainage, followed by crushed stone bound with mortar, then gravel cemented with clay, and finally interlocking volcanic rock slabs cambered to shed water. This meticulous system kept armies marching and goods flowing year-round, while medieval Europe's paths became impassable for months each winter. The difference wasn't just convenience, it was the lifeblood of civilization itself slipping away. What made these roads revolutionary was their systematic approach to problems medieval engineers would struggle with for centuries. Roman surveyors used tools called grommet to plot perfectly straight routes across valleys and hills, digging tunnels when necessary. Curved surfaces channeled rainwater into stone gutters, while mile markers and way stations provided rest and navigation. Most impressively, the roads self-repaired. Their flexible layered structure allowed ground movement without cracking, a technique modern engineers call unbound aggregate. When the Anglo-Saxon Chronicle described 9th century English roads as slaughterous pits, it wasn't poetic exaggeration without Roman methods. Transport had regressed to a dangerous seasonal ordeal. Imagine the impact if these techniques had survived. Medieval trade caravans could have moved at Roman speeds, about 25 miles per day versus the typical 8, slashing the time and cost of moving goods. The Hanseatic League's network might have spanned further than coastal cities, knitting together inland markets. Crusaders wouldn't have wasted months slogging to ports. Reinforcements could reach besieged castles in days rather than weeks. Even ideas would have traveled faster, books, news, and innovations spreading at a pace closer to the Roman cursus publicus, their state-run courier system that relayed messages from Britain to Syria in under a month. The loss went beyond transportation. Roman roads were economic engines lined with inns, blacksmiths, and markets that thrived on passing traffic. Medieval villages cut off by terrible roads often starved amidst plenty because they couldn't trade surplus harvests. When the Black Death hit in the 1300s, slow communication meant quarantines were imposed too late, a problem the Romans had mitigated with their rapid dispatch riders. Even the feudal system itself might have weakened earlier with better roads, as serfs could more easily flee oppressive manners for towns. Yet fragments of this knowledge persisted in unlikely places. Byzantine engineers maintained portions of the Via Egnatia into the Middle Ages, and Islamic caliphates adopted Roman surveying techniques for their own roads. The real tragedy was the disconnect. While a few still walked on ancient pavement, no one remembered how to build it anew. When Napoleon ordered his famous roads in the 1800s, his engineers essentially reinvented Roman methods from scratch, unaware they were echoing a 2,000-year-old playbook. The most enduring lesson of Rome's roads isn't about stone or drainage. It's about how quickly even the mightiest infrastructure can vanish when the knowledge behind it slips away. What took centuries to build was lost in just a few generations, leaving the medieval world to wander in circles until it rediscovered the straight path forward. In the hands of a Viking warrior, an Ulfberht sword wasn't just a weapon. It was a masterpiece of metallurgy that defied the limits of its time. Forged between the 9th and 11th centuries, these blades bore the enigmatic + Ulfberht + T inscription, a mark of quality so revered it was often imitated but never duplicated. What set them apart wasn't just craftsmanship, it was the material itself. While most medieval swords were made from brittle, impure iron prone to snapping in battle, Ulfberht's contained crucible steel with a carbon content nearing modern standards, creating blades that were lighter, sharper, and nearly unbreakable. The secret, a supply chain stretching thousands of miles to the east, where Persian and Indian smelters had perfected high-temperature steel production centuries before Europe. When this trade route collapsed, the knowledge vanished with it, leaving warriors to fight with inferior metal for generations. The mystery of Ulfberht steel begins with its origins. Chemical analysis reveals trace elements like vanadium and molybdenum metals found not in European soil, but in Central Asian ores. Islamic geographers like al-Biruni documented Indian furnaces reaching temperatures over 1,500 degrees Celsius, hot enough to purify iron into high-carbon steel. Viking traders likely acquired these ingots along the Volga trade routes, transporting them back to workshops where Norse smiths forged them into legendary blades. The result was a sword that could bend 90 degrees and spring back straight, its edge holding sharpness through battle after battle. Contemporary accounts describe Ulfberht's cleaving helmets and shields like parchment, while lesser swords shattered against them. Yet this technological edge was fleeting. The collapse of the Silk Road and political upheavals in the Islamic world severed the supply of crucible steel by the 1200s. European smiths, lacking both the raw materials and the technical knowledge to replicate the process, regressed to bloomery iron, a porous, slag-filled metal that required heavy, unwieldy blades to compensate for weakness. The difference was stark. A typical medieval longsword weighed nearly 3 pounds, while an Ulfberht of similar length weighed just 2, yet outperformed it in every way. The loss wasn't just aesthetic, it was tactical. Lighter, stronger swords would have allowed knights greater speed and endurance in combat, potentially altering the outcomes of clashes from the Crusades to Agincourt. What makes the Ulfberht's disappearance so haunting is how close Europe came to preserving its secrets. A handful of medieval manuscripts, like the 12th century Mappi Clavicula, contain vague references to Eastern steel working, but without detailed instructions or access to the right ores, the knowledge remained out of reach. Even Toledo and Damascus, later renowned for their blades, never quite matched the Ulfberht's purity. It wasn't until the 1800s that European metallurgists rediscovered crucible steel, finally closing a gap that had lasted nearly a millennium. The legacy of these swords isn't just about superior weaponry, it's a lesson in the fragility of globalized technology. The Ulfberht wasn't lost due to lack of skill, but because the network that sustained it unraveled. In a world without backup systems or widespread literacy, even the mightiest innovations could vanish when trade routes faltered. Had just one Norse smith recorded the recipe, or had a single shipment of steel ingots reached a European monastery's forge, the course of medieval warfare, and perhaps history itself might have swung on the edge of a sharper blade. In the heart of 9th century, Baghdad stood a beacon of knowledge so vast, it made Europe's greatest monasteries look like village schoolhouses, the legendary House of Wisdom. Founded by Caliph Harun al-Rashid and expanded by his son al-Mamun, this wasn't just a library, it was the internet of the medieval world, where scholars from every corner of the empire gathered to translate, debate, and innovate. Greek philosophy met Indian mathematics under its domed ceilings, while Persian medicine mingled with Chinese astronomy. But in 1258, the Mongol siege didn't just topple a city, it erased centuries of accumulated wisdom in a single catastrophic event. When Hulagu Khan's armies threw the House of Wisdom's manuscripts into the Tigris River, historians say the waters ran black with ink for months. The loss wasn't just cultural, it was a wound to human progress itself. What made this institution extraordinary was its systematic approach to preserving knowledge. Teams of multilingual scholars, Christians, Jews, Muslims, and Sabians worked side by side translating texts into Arabic. Ptolemy's Almagest, Euclid's Elements, even Sanskrit works on algebra and trigonometry were meticulously copied and annotated. The mathematician Al-Khwarizmi developed algebra here, giving the world the very word algorithm. Physician Al-Razi compiled medical encyclopedias that would influence Europe for centuries, while astronomer Al-Battani calculated the solar year to within minutes of modern measurements. This was more than storage, it was active scholarship pushing boundaries. Had these texts reached medieval Europe intact, universities like Oxford and Bologna might have leapfrogged past centuries of trial and error. Instead, Western scholars spent generations rediscovering what Baghdad had already known. The Mongol destruction wasn't just about burned parchment, it severed critical transmission chains. Consider mathematics. While Fibonacci introduced Arabic numerals to Europe in 1200, crucial works on calculus precursors and spherical trigonometry never made the journey. Medicine regressed too. Al-Razi's distinction between measles and smallpox had to be painstakingly relearned, costing countless lives. Most tragically, the house's collaborative model itself was lost. Unlike European monasteries where knowledge was often hoarded, Baghdad scholars believed in open exchange, maintaining correspondence networks from Cordoba to Samarkand. For a brief moment, the world had glimpsed how shared knowledge could accelerate progress until the flames consumed that vision, yet fragments survived. Some texts had been copied and sent to Toledo before the fall, where Latin translations trickled into Europe. Others were preserved in Damascus and Istanbul, waiting for the Renaissance to rediscover them. The real tragedy lies in what we'll never know, the original works that contained ideas too advanced for their time, lost before they could inspire future generations. When Hylogu's soldiers reportedly used the house's shelves as firewood, they weren't just burning books, they were burning bridges to potential futures where science might have flourished centuries earlier. The House of Wisdom stands as history's greatest warning that civilization's greatest treasures aren't gold or land, but the fragile pages that contain the sum of human thought. When Roman legions finally breached Carthage's walls in 146 BCE, they didn't just destroy a city, they erased an agricultural revolution. Among the countless scrolls tossed into the flames were the Carthaginians' meticulously compiled farming manuals, volumes detailing crop rotations, irrigation systems, and soil enrichment techniques so advanced, medieval Europe wouldn't rediscover them for over 1,000 years. These weren't just notes, they were the culmination of centuries of North African innovation, where arid lands bloomed with orchards and grain fields through methods far beyond the crude two-field system later used by medieval peasants. The tragedy wasn't just the loss of knowledge, it was the famines and failed harvests that followed, crises that might have been avoided if Rome hadn't prioritized vengeance over wisdom. Carthage's agricultural prowess was legendary even to its enemies. Greek historian Diodorus Siculus described vast gardens of Hesperides stretching beyond the city walls, fed by intricate networks of cisterns and terraces that maximized every drop of water. Their manuals reportedly covered everything from grafting fruit trees to creating compost from fish waste, a practice modern science confirms dramatically boosts soil nitrogen. Most revolutionary was their 4-crop rotation system, alternating cereals with legumes, olives, and fallow periods to prevent soil exhaustion. Compare this to medieval Europe, where farmers repeatedly planted wheat until the land turned barren, then prayed for divine intervention. The difference wasn't just yield, it was food security. Carthaginian silos could stockpile 7 years' worth of grain, while medieval villages teetered on the brink of starvation after a single bad harvest. The ripple effects of this lost knowledge are heartbreaking to trace. When the Little Ice Age struck in the 1300s, freezing fields across Europe, farmers had no fallback strategies. They watched helplessly as topsoil blew away or crops rotted in endless rain problems Carthaginian texts had already solved with techniques like contour plowing and windbreak planting. Even basic innovations were missing. Medieval peasants didn't realize legumes restored soil fertility until the 1700s, though Carthaginian manuals had spelled it out centuries before. The worst toll was human. Historians estimate over 25 million died in the Great Famine of 1315 to 1317, a catastrophe that might have been mitigated with access to Carthage's preserved wisdom. Yet fragments survived in unexpected ways. Some techniques likely passed to Moorish Spain, where Arab agronomists like Ibn Basil wrote treatises echoing Carthaginian methods. The Byzantines, too, preserved snippets in their Geoponica farming guides that made their way to Italian monasteries. But without the full systematic knowledge, these pieces remained disjointed, like trying to rebuild an engine from a handful of gears. The real loss wasn't just individual techniques. It was the underlying philosophy of sustainable agriculture that viewed farming as a science rather than a struggle against nature. The burning of Carthage libraries wasn't just an act of war, it was a theft from future generations. Those scrolls could have taught medieval Europe how to feed itself through droughts and frosts, how to turn marshlands into fertile fields, how to prevent the soil exhaustion that still plagues modern agriculture. Instead, farmers had to relearn everything the hard way through centuries of trial and error. When we read about Roman soldiers throwing Carthaginian books into bonfires, we're not just witnessing the destruction of paper, we're watching the flames consume answers to hunger itself, leaving the medieval world to starve in ignorance of solutions that had already been written. While medieval Europeans sweltered in stone houses that trapped heat like ovens, Song Dynasty architects in China had already mastered the art of natural air conditioning without a single moving part. The secret lay in skywells, ingenious courtyard openings designed like inverted chimneys that pulled cool air through buildings while venting hot air upward. These weren't just architectural flourishes, they were precision-engineered climate control systems, regulating temperature and humidity with nothing but geometry and airflow. In regions where summer temperatures routinely soared above 100 degrees, skywell-equipped homes remained a comfortable 75, a feat European medicine would later attribute to miasma rather than physics. The brilliance of skywells lay in their layered design. Narrow openings at ground level channeled breezes into the structure, while the central courtyard's open roof created a low-pressure zone that sucked hot air upward like a natural exhaust fan. Brick walls with porous, breathing mortar absorbed moisture during humid months, then released it in dry periods to stabilize indoor conditions. Some wealthy households even added water features beneath the skywell, using evaporative cooling to drop temperatures further, a technique modern architects are only now rediscovering as sustainable design. Compared to Europe's solution stuffing herbs in windows to mask the stench of sweat and mildew, this was space-age thinking in the 1200s. Had this technology crossed the Silk Road, it could have reshaped European cities during their most vulnerable centuries. The Black Death thrived in cramped, overheated dwellings where fleas and bacteria multiplied unchecked. Skywell ventilation might have disrupted this cycle, creating healthier indoor environments long before germ theory explained why. Venetian merchants trading with the East occasionally described these wind courtyards, but without understanding the physics behind them, European builders dismissed the concept as exotic ornamentation. The irony, Gothic cathedrals used similar principles in their towering naves to vent candle smoke, proof the basic science was within reach if only someone had connected the dots. Beyond comfort, skywells offered hidden benefits medieval Europe desperately needed. Moldering manuscripts in damp monasteries could have been preserved in skywell-regulated scriptoria, while apothecaries might have kept delicate herbs potent in dry, cool storerooms. Even social structures could have shifted without the need to escape sweltering homes. The tradition of summer retreats to country estates might never have taken root, keeping urban populations more stable year-round. The real tragedy isn't that Europe lacked the technology, it's that the knowledge languished just a continent away, waiting for someone to recognize its value. Today, as engineers grapple with energy-guzzling HVAC systems, skywell principles are making a comeback in eco-friendly designs. But the 14th century gap between invention and rediscovery speaks volumes about how geography and cultural blind spots can stall progress. For all the talk of medieval stagnation, the truth is more frustrating. Many solutions already existed, if only they'd been given the chance to spread. The skywell stands as a monument not to what was impossible, but to what was overlooked, a whisper of cooler, smarter living that Europe simply wasn't listening for. High in the Andes, Inca administrators kept track of millions taxes, census data, even epic poems without writing a single word. Instead, they used Quipus' intricate arrangements of knotted strings that encoded information through colors, knot positions, and chord twists. To the Spanish conquistadors who burned them as pagan artifacts, these were mere curiosities. But modern researchers now believe Quipus may have been as sophisticated as early cuneiform, a three-dimensional writing system that could have revolutionized medieval record-keeping if it had crossed the Atlantic. What made Quipus revolutionary wasn't just their form, it was their scalability. A single quipu could track harvests across an empire spanning 2,000 miles, with knots representing numbers in a base 10 system, and colors denoting categories like corn, potatoes, or llama herds. Some chords even had subsidiary strings branching off like tree limbs, creating nested hierarchies of data. Spanish chroniclers reported Inca officials arriving with quipus that contained decades of astronomical observations, suggesting they weren't just ledgers but historical archives. Compare this to medieval Europe's parchment scrolls, expensive, perishable, and requiring literate scribes, and the advantage becomes clear. Quipus were lightweight, durable, and could be read by trained officials regardless of native language. The tragedy of their destruction goes beyond lost historical records. Quipus represented a completely different approach to information storage, one that might have inspired hybrid systems in medieval Europe. Picture Cistercian monasteries using knot-based accounting to track tithes, or Venetian merchants encoding trade deals in colored threads that couldn't be forged like ink signatures. Even more tantalizing is the possibility that quipus could have evolved. Recent studies at Harvard's Quipu database project suggest some knots may represent syllabic sounds, hinting at a full writing system nipped in the bud. Had Spanish priests preserved rather than burned them, linguists might have cracked the code centuries ago, proving that writing doesn't require ink to be literate. The Quipu's loss wasn't just cultural, it was a missed opportunity to diversify how humanity records thought. Medieval Europe clung to alphabets as the sole path to knowledge, dismissing alternatives as primitive. Yet the Inca system solved problems Europeans struggled with for centuries: how to make records portable in rainy climates, how to compute large sums without paper, how to transmit data across language barriers. When a single spark from a Spanish torch could erase generations of administrative wisdom, it revealed the fragility of all non-written knowledge and how much richer our shared history might be if we'd allowed more than one way to tie the threads of memory. While European lords draped wet tapestries over doorways in a futile attempt to beat the heat, Persian architects had already turned entire cities into natural refrigerators. Their secret, the wind-catcher elegant towers rising from rooftops like slender chimneys, designed not to emit smoke, but to capture even the faintest breeze and funnel it downward into homes. In cities like Yazd, where summer temperatures regularly soared past 120 degrees, these ingenious structures could cool interior spaces by up to 40 degrees without a single drop of water or ounce of fuel. Medieval travelers from Europe described them as magic flutes that sang with cold air, never grasping the simple physics that made them work, or realizing their own sweltering castles could have been transformed with the same principles. The genius of wind catchers lay in their adaptability. Some featured adjustable vents to direct airflow, while others had internal damp cloth screens for evaporative cooling, primitive humidifiers that made dry desert air feel refreshing. Multi-directional designs caught cross breezes no matter which way the wind blew, and underground tunnels called kanats often paired with them, circulating air that had been naturally chilled by the earth. The result was a passive cooling system so effective that ice could be stored in underground chambers even during scorching summers, a luxury Europeans couldn't replicate until the invention of artificial refrigeration in the 1800s. Had this technology migrated westward during the Crusades or through Moorish Spain, the stifling stone keeps of medieval Europe might have become livable year-round. Monasteries could have preserved delicate manuscripts in cool, dry scriptoria instead of battling mold and pests. Apothecaries might have kept temperature-sensitive remedies potent for longer, revolutionizing medieval medicine. Even the social fabric could have shifted. Without the need to escape to cooler countryside estates during summer months, urban centers might have maintained stable populations, accelerating economic and intellectual exchange. The windcatcher's absence in Europe wasn't due to complexity. The basic design, a tower with internal baffles to direct airflow, was well within the capabilities of Gothic stonemasons. The real barrier was cultural. European architects saw ventilation as an afterthought, prioritizing defensibility over comfort. When Venetian merchants brought back sketches of Persian windcatchers, they were dismissed as exotic oddities rather than viable solutions. By the time colonial powers rediscovered them in the 19th century, they were viewed as quaint relics, not the masterpieces of sustainable engineering they truly were. Today, as modern architects struggle with energy-intensive air conditioning, windcatchers are experiencing a revival in eco-friendly designs. But the 8th century gap between their heyday and their rediscovery speaks volumes about how innovation can languish in isolation. For all the talk of medieval technological stagnation, the truth is more frustrating. Many solutions were already at hand, if only someone had thought to look beyond the horizon. The windcatcher stands as a testament not to what couldn't be done, but to what wasn't shared, a whisper of cooler, smarter living that Europe never thought to hear. While medieval Europeans drew water from stagnant wells crawling with disease, Roman citizens 1,000 years earlier had enjoyed crystal-clear streams flowing into their homes through a network of engineering marvels, aqueducts. These weren't just stone channels, they were precision-designed water highways, some spanning over 50 miles with gradients so slight they dropped only a few inches every 100 feet. The Romans didn't just move water, they mastered it, using sedimentation tanks to filter out impurities and inverted siphons to cross valleys without losing pressure. When this knowledge crumbled alongside the empire, the consequences were dire. Medieval London's Thames became an open sewer, while Parisians drank from the Seine alongside rotting carcasses. The gap between Roman hygiene and medieval survival wasn't just a step back, it was a plunge into centuries of preventable epidemics. The sophistication of Roman hydraulics puts medieval efforts to shame. Lead pipes fitted with bronze valves delivered water directly to public fountains, bathhouses, and even wealthy homes, all regulated by a system of sluice gates and distribution tanks. Engineers like Sextus Julius Frontinus wrote entire manuals on flow rates and maintenance, calculating water needs down to the last amphora. Compare this to the 1300s, when London's great conduit, a single lead pipe fed by a spring, served 30,000 people, its water tainted by the leather and pitch used to seal joints. The Romans had solved these problems with welded lead seams and animal fat lubricants, techniques lost to the Dark Ages. But the real tragedy wasn't just the loss of clean water, it was the cascading failures it caused. Without aqueducts, medieval cities couldn't support large populations, stifling economic growth. Public baths, once hubs of social and hygienic life, vanished, contributing to the flea-ridden conditions that fueled the Black Death. Even firefighting became nearly impossible. Rome's pressurized aqueducts fed street-side hydrants, while medieval towns burned to ashes waiting for bucket brigades. The knowledge hadn't completely vanished. Byzantine Constantinople maintained its aqueducts into the Middle Ages, and Moorish Cordoba built new ones, but Europe's fractured kingdoms lacked the resources or organizational skills to replicate Rome's systemic approach. What's most striking is how close medieval Europe came to rediscovering these principles. Cistercian monks built sophisticated water wheels and drainage systems for their monasteries, while Venetian engineers revived Roman techniques for their canals. Yet without the underlying mathematical framework, Vitruvius's formulas for gradient calculations or Hero of Alexandria's studies on siphon physics, these remained piecemeal solutions. When Pope Nicholas V finally ordered the repair of Rome's Aqua Virgo in 1453, workers had to reverse engineer the ruins, unaware they were standing on the blueprint for a healthier future. The aqueducts weren't just stone and water, they were the lifeblood of civilization itself, and their absence left the medieval world gasping for air. Hidden in a vault at Yale University lies what might be the most baffling book in human history, the Voynich Manuscript. This 200-page medieval codex, carbon dated to the early 1500s, is filled with looping, alien script that has resisted every attempt at translation for over a century. But the real mystery isn't just the unreadable text, it's the bizarre illustrations crowding its vellum pages. Naked women bathing in green liquid, constellations that match no known sky, and plants so fantastical they seem plucked from a fever dream. To modern eyes, it looks like a biologist's notebook crossed with an alchemist's daydream. If only we could read a single word. What sets the Voynich apart from other cryptic texts is its sheer complexity. Statistical analysis reveals patterns matching natural language's words with predictable letter repetitions, sentence structures that suggest grammar, yet it defies all known linguistic families. The illustrations deepen the enigma. Herbal sections depict flora with twisted roots and leaves found nowhere on Earth, while astronomical diagrams show celestial spheres connected by tubes like some medieval vision of quantum entanglement. Most haunting are the so-called biological pages, where humanoid figures float in intricate networks of vessels, their meaning hovering just beyond comprehension. This isn't random scribbling, it's a systematic presentation of knowledge we no longer recognize. Theories about its origins range from plausible to outlandish. Some scholars argue it's a lost treatise on protochemistry, with the plants representing laboratory apparatus and the green bath symbolizing distillation processes. Others see it as a sophisticated hoax, though why anyone would craft such an elaborate fake centuries before forgery became profitable remains unclear. The most tantalizing possibility, that it preserves fragments of a forgotten scientific tradition, one that viewed nature through a lens so different from ours that its very language is now indecipherable. Medieval Arab scholars like Al-Kindi wrote about cryptographic techniques, and Roger Bacon, a contemporary of the manuscript's likely creation, experimented with encoded knowledge. Could the Voynich be a time capsule from an alternate path of inquiry, one that blended optics, botany, and anatomy in ways modernity never pursued? Decoding it could rewrite our understanding of medieval science. Those peculiar plants might document extinct species or early genetic engineering attempts. The astrological charts could reveal lost observations of supernova or comets. Even the nonsense text may hold medicinal recipes or mathematical concepts suppressed by religious authorities. The cost of its obscurity becomes painfully clear when you consider how much was already being erased in the 1500s burned Mayan codices, scattered Islamic medical texts, Gnostic gospels torn apart by censors. The Voynich might be the sole survivor of an intellectual current we didn't even know existed. Modern technology has only deepened the mystery. AI, Analysis in 2017 suggested possible links to Hebrew and Arabic, while multispectral imaging revealed faint underdrawings beneath the ink, proof of careful planning rather than gibberish. Yet the core truth remains. Here sits a book that someone, somewhere, 500 years ago deemed vital enough to painstakingly transcribe, filled with knowledge that evaporated somewhere between then and now. Whether it's an encrypted herbal, an alien artifact, or the world's most elaborate inside joke, the Voynich Manuscript stands as a monument to how much we still don't know about the past, and how many ideas may have slipped through history's cracks without leaving even a whisper behind. While medieval stonemasons struggled to hoist blocks with ropes and pulleys, Roman engineers had already perfected the ultimate medieval forklift, the treadwheel crane. Powered not by steam or beasts, but by human laborers walking inside giant hamster wheel-like mechanisms, these machines could lift several tons with precision, turning back-breaking labor into a feat of engineering finesse. Capable of lifting stones weighing over 6 tons to heights of 30 feet, Roman cranes built the Colosseum and Pantheon with an efficiency that wouldn't be matched again until the Gothic cathedrals of the 1200s. The gap between these two peaks nearly a millennium long wasn't just a pause in progress. It was a regression that left Europe struggling to move mountains one rock at a time. The brilliance of the treadwheel crane lay in its mechanical advantage. A single worker walking inside the wheel could lift loads 20 times heavier than by hand, thanks to a system of gears and pulleys that multiplied force. Unlike medieval cranes, which relied on sheer manpower to turn windlasses, the Roman design distributed weight evenly, allowing smaller teams to handle massive blocks without snapping ropes or collapsing wooden frames. Archaeologists have found evidence of these cranes across the empire, from the harbor at Ostia, where they loaded ships with marble, to the quarries of Tivoli, where they lifted raw stone straight from the pits. Yet after Rome's fall, the technology fragmented, surviving only in cryptic manuscripts and the occasional Byzantine dockyard. Imagine how differently medieval cities might have risen if these cranes had remained commonplace. Gothic architects spent decades hoisting flying buttresses into place with precarious winches, a process that could have been halved with Roman engineering. Castle construction, often delayed for years due to slow stone lifting, might have accelerated, allowing lords to fortify borders faster against invaders. Even shipbuilding could have transformed. Venetian arsenals might have launched galleys in months instead of years with crane-assisted hull assembly. The ripple effects go beyond speed. Fewer workers would have died in collapses or rope failures, and projects like London Bridge or Mont St. Michel might have been completed generations earlier. What's most striking is how close medieval Europe came to rediscovering this technology independently. Villard de Honnecourt, the 13th century architect whose sketchbook survives as a treasure trove of Gothic engineering, drew detailed crane designs eerily similar to Roman models. Yet without access to ancient technical manuals, builders had to reinvent the wheel quite literally through trial and error. By the time treadwheel cranes reappeared on cathedral sites, they were hailed as innovations, their Roman ancestors long forgotten. The delay wasn't due to lack of need or skill, but to the severed thread of knowledge that left later generations solving problems their predecessors had already cracked. The treadwheel crane story is a testament to how much infrastructure depends on shared wisdom. When Rome's engineering corps dissolved, so too did the institutional knowledge of load distributions, gear ratios, and safety protocols. Medieval craftsmen, no less brilliant than their Roman counterparts, had to rebuild this expertise from scratch, wasting centuries on solutions hiding in plain sight among the ruins. Today, as modern cranes swing skyscrapers into place, they owe an unacknowledged debt to those ancient wheels, proof that progress isn't just about moving forward, but remembering what came before. Centuries before European knights faced the terror of gunpowder, Chinese soldiers were already wielding something far more fearsome, a weapon that spat liquid fire with the precision of a dragon's breath. The Song Dynasty's fierce fire oil sprayer wasn't just an early flamethrower, it was a piston-powered marvel that could shoot blazing streams of naphtha over 30 feet, engulfing enemies in unstoppable flames. Unlike the static Greek fire of Byzantium, these were mobile units, carried by teams of soldiers who pumped pressurized tanks like giant bellows to unleash hellfire on demand. Forged during the 1000s, this technology represented a terrifying leap in warfare, one that could have shortcut centuries of gunpowder experimentation if it had reached Europe before the age of cannons. The mechanics behind these devices were shockingly advanced. Bamboo tubes reinforced with iron hooves acted as barrels, while dual piston pumps, a design later echoed in Renaissance air rifles, created continuous bursts of flaming fuel. Historians from the Song military manual Wujing Zongyao describe crews wearing fire-resistant suits made of wet leather, advancing behind portable fire shields as they drenched fortifications in burning oil. What made these weapons truly revolutionary wasn't just their destructiveness, but their adaptability. Some versions mixed powdered lime into the fuel, creating chemical fires that water only intensified, a brutal innovation medieval Europe wouldn't encounter until the Italian wars of the 1500s. Had these flamethrowers spread westward along the Silk Road, the evolution of firearms might have taken a radically different path. Picture Crusader armies storming Jerusalem with backpack-mounted flame projectors, or Mongol hordes deploying mobile fire units alongside their horse archers. The psychological impact alone would have rewritten medieval tactics. Castle walls, the pinnacle of European defense, would have become death traps against weapons that turned stone into furnaces. Even more critically, the metallurgy and pressure systems developed for these devices could have accelerated gunpowder technology. The same piston mechanisms perfecting liquid fire might have been repurposed for early cartridge systems, potentially leading to handheld firearms centuries before the arquebus. Yet the technology stalled in isolation. While Song engineers refined their designs into multi-barreled fire lances that eventually led to gunpowder rockets, Europe remained oblivious. By the time Western knights encountered gunpowder, it came in the form of crude cannons, a full 300 years after Chinese armies had mastered controlled flame projection. The delay wasn't due to lack of interest. Marco Polo's accounts of Chinese fire weapons were dismissed as tall tales, but to the fragility of knowledge transmission across continents. What makes this loss especially poignant is how close the pieces came to connecting. Arab chemists in Moorish Spain experimented with naphtha-based weapons, while Byzantine refugees fleeing the Fourth Crusade brought fragments of Greek fire knowledge to Italy. Had any trader or mercenary bridged the gap between these traditions, the battlefields of the 1300s might have been illuminated not by the occasional cannon's flash, but by the relentless roar of mechanized fire. Instead, the flamethrower became another ghost in the arsenal of history, a reminder that even the most terrifying innovations can fade when the world isn't ready to catch the spark. In the candlelit courts of 13th century Damascus, a mechanical elephant carved from brass and wood turned its head, trumpeted through a hollow reed, and dropped a tiny metal ball into a vase, all without a single human touch. This was no sorcery, but the masterpiece of engineer Ismail al-Jazari, whose book of knowledge of ingenious mechanical devices documented dozens of such automata, from water-powered musicians to castle clocks animated by intricate gear trains. What makes these creations astonishing isn't just their complexity, but how close they came to sparking an industrial revolution 8 centuries early. While medieval Europe saw them as mere curiosities, these machines contained the DNA of robotics, hydraulics, and programmable logic, if only someone had recognized their potential beyond entertainment. Al-Jazari's elephant clock alone was a marvel of interdisciplinary engineering. Powered by a concealed water tank, it used hydraulic principles to mark time with uncanny precision. A floating bowl inside the elephant's howdah filled at a constant rate, triggering a series of levers that moved figurines, a scribe pointing to the hour, a falcon dropping balls into a vase to count minutes. The entire system self-reset every half hour when the bowl sank, pulling ropes that rotated a platform beneath the elephant. This wasn't just a clock, it was a mechanical computer, anticipating concepts like feedback loops and escapement mechanisms that wouldn't become standard in Europe until the 1400s. Had these principles been scaled beyond palace novelties, they could have revolutionized everything from textile mills to agricultural irrigation. The tragedy lies in what these automata almost became. Al-Jazari's designs included camshafts and crankshafts, components essential to modern engines, yet medieval workshops lacked the infrastructure to mass-produce them. His programmable boat with 4 robotic musicians used pegged cylinders to remember musical sequences, a precursor to punch card programming used in 19th century looms. Even more striking was his water-raising device, which converted rotary motion into linear motion using a crank slider mechanism identical to those in today's car engines. These weren't dead ends, they were prototypes abandoned for lack of vision. While European nobles gawked at mechanical angels in cathedral clocks, the underlying technology languished as amusement rather than innovation. Imagine an alternate timeline where these ideas took root. Factories powered by hydraulic automata could have mechanized paper production or grain milling centuries before the spinning jenny. Al-Jazari's chain pump used in his castle clocks to circulate water might have drained medieval mines or irrigated fields on an industrial scale. Even warfare could have transformed. His designs for automated gates and lifting devices could have evolved into siege engines with mechanical reloading systems. The gap between these possibilities and reality wasn't technical, it was cultural. In a world where labor was cheap and muscle power abundant, few saw the value in replacing humans with machines. Yet fragments of this knowledge persisted in unexpected ways. Leonardo da Vinci's notebooks echo Al-Jazari's gear systems, while the intricate clocks of Prague and Strasbourg borrowed his weight-driven mechanisms. The real loss wasn't the machines themselves, but the mindset they represented, a vision of technology as more than imitation of life, but as a way to transcend its limits. When modern roboticists study Al-Jazari's work, they're not just examining historical artifacts, they're confronting a road not taken, one where the age of automation might have dawned not in smoky 19th century factories, but in the sunlit courtyards of medieval Damascus. His elephant clock still ticks in replicas today, a reminder that the past wasn't just preparing for the future, it was inventing it, then leaving the blueprints where few would think to look. The disappearance of these groundbreaking technologies wasn't just bad luck, it was the collision of human flaws and historical chaos. War acted like a black hole for innovation, swallowing entire libraries in moments of conquest. When Mongol armies sacked Baghdad in 1258, they didn't just topple a city, they erased the House of Wisdom, a repository of knowledge so vast it made Europe's greatest libraries look like pamphlet collections. Centuries of Persian, Greek, and Indian scholarship vanished into the Tigris River, its ink-darkened waters symbolizing how quickly brilliance can dissolve into nothingness. But violence wasn't the only thief. Some secrets were deliberately buried, like the Byzantine Empire's obsessive guarding of Greek fire's formula, where leaking the recipe was punishable by death. Their paranoia preserved military advantage but robbed humanity of chemical insights that might have accelerated industrial progress by half a millennium. Even without conflict or secrecy, knowledge proved heartbreakingly fragile. The Roman Empire's collapse didn't just shatter political unity, it fractured the intricate networks of apprenticeship and documentation that kept advanced engineering alive. Master stonemasons who could calculate concrete ratios or aqueduct gradients died without passing on their skills, leaving medieval builders to reverse engineer ruins they couldn't comprehend. Oral traditions fared no better. Viking sunstone navigation techniques, never written down, faded with the last shipwrights who understood how to calibrate crystals to polarized light. What makes these losses especially cruel is how close some came to surviving. Fragments of Roman engineering manuals made it to monastic scriptoria, but without the living context of working engineers, scribes copied diagrams of cranes and hypocausts as curiosities rather than blueprints for reconstruction. The medieval world's information bottleneck reliance on scarce, expensive manuscripts meant even preserved knowledge often languished unread. A single copy of Hero of Alexandria's Pneumatica, detailing steam engines and mechanical automata, gathered dust in a Constantinople monastery for centuries before being rediscovered too late to influence the Renaissance. Meanwhile, the Church's monopoly on literacy created perverse incentives. Some monasteries hoarded texts like dragons guarding gold, prioritizing theological works over pagan science. When the printing press finally arrived in the 1400s, it came centuries too late for technologies like Damascus steel forging or the Antikythera Mechanism's gear systems, their secrets already reduced to cryptic references in crumbling scrolls. Perhaps most tragically, some innovations vanished simply because they were too far ahead of their time. Hero's steam engine fascinated dinner guests but found no practical application in a slave-based economy. The Baghdad battery's tingling shocks were dismissed as a party trick rather than recognized as the birth of electrochemistry. These weren't failures of invention, they were failures of imagination, where societies lacked the frameworks to recognize their own breakthroughs. The printing press might have saved them, but by then, the craftsmen who could explain how to replicate them were dust, their workshops reclaimed by forests or farmland. The real lesson isn't just that knowledge can disappear, it's that progress requires more than brilliant ideas. It needs entire ecosystems of preservation, transmission, and vision to keep those ideas alive long enough for the world to catch up. These lost marvels of the ancient and medieval world stand as stark reminders progress isn't a straight line, but a winding path littered with forgotten breakthroughs. Each of these 25 technologies represents a fork in history's road, a moment when civilization could have leaped forward but instead stumbled back into the dark. The difference between our timeline and one where these inventions thrived isn't just a matter of gadgets appearing earlier, it's about how their survival might have reshaped entire societies. Imagine a Middle Ages where Roman concrete kept cities dry and disease-free, where steam-powered mills freed peasants from backbreaking labor, where Damascus steel tools made farming twice as efficient. The ripple effects would have touched everything from lifespans to literacy rates, from the height of cathedrals to the reach of empires. What's most haunting isn't just the loss of the technologies themselves, but the mindsets they represented. The Antikythera Mechanism proves the ancients could think in gears and algorithms centuries before the scientific method. The Baghdad battery suggests someone glimpsed the potential of electricity long before it was understood. These weren't just clever toys, they were flickering glimpses of alternate futures, snuffed out by war, secrecy, or simple lack of vision. The real tragedy is how many times humanity had to reinvent the wheel, literally, because the original blueprints were lost to time. This isn't just about admiring ancient genius, it's a warning. In an age where knowledge feels permanent, stored in clouds and backups, we forget how easily expertise can evaporate. The Library of Alexandria seemed eternal until it burned. The master smiths of Damascus steel thought their craft would endure forever until it didn't. Our own breakthroughs might be just as fragile if we don't actively preserve and build upon them. So which of these lost wonders resonates most with you? Would you trade modern computers for a world where Hero's steam engine kicked off an industrial revolution in ancient Rome? Might the survival of Greek fire have changed the balance of power between East and West? The comment section is your time machine. Share which technology you'd resurrect and why. And if you've enjoyed this journey through history's forgotten toolbox, consider subscribing. We're just scratching the surface of the hidden innovations that could have, and perhaps should have, changed everything. The past is full of roads not taken, and together we'll keep exploring them.